Everybody, thank you for coming to this school seminar, the next talk in the series, which is given today by Dr. Rebecca Carey. Before I introduce her further, I would like to remind you all that we live in a wonderful country that was standard for by the Aboriginal people of Australia, and we perpetuate, tradition as we meet on land. And so here in Canberra, we're on the land of the Ngambri and Ngunnawal people. And so I extend my respects to their elders, past, present, and emerging. So today in our seminar series, we have Dr. Rebecca Carey. She's coming all the way from the University of Tasmania. Rebecca is a volcanologist, an associate professor at University of Tasmania, and she's also an ARC fellow. She's very much interested into submarine volcanoes at the moment, and potentially their links to mineral deposits, and all those wonderful, valuable minerals, critical minerals that Australia and the world need. Throughout her career, she's been traveling a little bit around the world. We can put Hawaii, we can put San Francisco, and Tasmania, a lovely little island that I'm sure lots of you have visited. And yeah, today she's going to talk to us about one of the biggest explosive volcanic eruption of our time, and I hope that you're all ready to listen to it. All right, so Rebecca, please go ahead.
Yes, okay. First of all, big thank you to Thomas and the invitation to present to you today at ANU, and also extending that thanks to Thomas, because he has accommodated all of our requests and touring the facilities here at ANU, which are incredible. So thank you so much, Thomas. I'm also here with some of my research group. So Rachel Baxter from University of Otago worked with James White, also on the voyage. Yes. Melis Moulin from Paris, new PhD student working on problems in submarine volcanology, and Maurizio, he's working on understanding the brecciation processes associated with breccia pipes in copper porphyry systems. So we're around for the rest of this afternoon and tomorrow. So yes, please come and talk to us. Okay, so right. So in August and September last year, we took Australia's research vessel, the RV Investigator, shown in this image, to Tonga. In the background, you can see the RV Investigator here, full ocean class vessel. And in the background is Hunga, which is a remnant island at the top of Hunga Volcano, which is a large submarine volcanic edifice as big as Mount Fuji. So the only part of this volcano that is identifiable on land is the two islands, Hunga and Hunga Tonga.
I think you might have to click on this one. Okay.
So this eruption is quite famous because it's the most powerful eruption of the century, possibly many centuries. It is an incredible eruption and very curious for lots of different reasons, which is why the scientific community across atmospheric sciences, oceanography, and earth sciences have really come together to try and understand this event. The curious thing for me is that this eruption was extremely powerful, yet the magma is andesitic in composition. Andesite magmas do not erupt in highly powerful explosive fashion. That's more common for the highly evolved magmas like rhyolites. This eruption plume entered the mesosphere, 57 kilometres, in about 47 minutes. That's about 60 metres a second of plume ascent velocity. It got to the mesosphere in 47 minutes or so, but the actual plume duration was 11 hours long at relatively high eruption rate. So we think from atmospheric observations around 10 to the 9 kilograms of material per second injected into the atmosphere. The other reason this eruption has garnered a lot of attention is the Pacific-wide tsunamis that inundated Tonga and the east coast of Australia, and the submarine sediment flows, which flowed along the seabed at 100, maybe 120 kilometres per hour, and severed the international and domestic seafloor communication cable that connects Tonga to the world. So there's a lot known about this eruption based on the atmospheric record and the eyewitness records from Tonga. This is a movie that was made by the Korean Polar Research Institute, which compares two different bathymetric surveys of the Hunga volcano. So this is what the volcano looked like in 2016. This is Hunga Hapai, this is Hunga Tonga, and in 2016 there was a sort of a landmass here that had a large crater. It's about 400 or 500 meters in diameter that connected these two islands. In the background, there's a crater, which is about 5 kilometers in diameter. And at this time, it's about 100 to 200 meters deep. And so I'm just going to play that movie here. So this is the 2016 survey from the Falcor. And this is the 2022 survey by the Korean ship. And you can see that there is now a giant hole at the summit of that volcano. That hole is 850 meters deep. The atmospheric fallout was calculated at about 1.5 cubic kilometers of material that went into the atmosphere and fell out. And so there's a missing 5.3 cubic kilometers of just the edifice. So that's just what we call the lithic volume, the volume of the edifice that has gone somewhere. And that's not accounting for the magma volume, which is derived from magma reservoirs deeper in the system. So it's hard to sort of understand what a cubic kilometre is. So I've converted to Melbourne cricket grounds. So the missing volume is about 2,800 Melbourne cricket ground volumes. So absolutely huge volume of material. So the atmospheric record has really been exhausted. Where that missing volume is and how this eruption manifests in terms of eruptive processes, that record is on the seafloor. And that's why we took the investigator to Tonga in order to collect some of those data sets to answer some really outstanding yet really fundamental first order questions about this eruption. So it was a multidisciplinary voyage. We had geophysicists on board, volcanologists, some geochemists, and of course the biologists. And the things that we collected here were about 4,800 kilometres of multi-beam bathymetry. So that's just mapping the seafloor. That mapping process also enables us to understand what the subsurface of the seafloor is. To depths, it varies, but to depths maybe of a few hundred metres. So we get kind of the sediment record with that profiling measurement. We collected 457 kilometres of multi-channel seismic reflection data. Eruption deposits, we were quite, some would say, excited about collecting cores during this voyage. So we collected 81 multi-cores, 81 deployments of the coring instrument. And that enables us to understand the top 60 centimetres of the sediment blanket, 16 giant piston cores, and we also dredged the caldera and collected some rocks. We also did some deep tow camera transects to understand what the seafloor looked like, how the biological community is recovering, and some CTD deployments to understand how water is moving in and out of that giant hole at the top of the volcano. One of our colleagues, Kathleen McKee, who's a geophysicist and a sort of an acoustic person, hydroacoustics, also put together a really beautiful time series of all the data that was available from this eruption, and some of that I'll be presenting today. Okay, so the first thing I need to do is provide a time series of the things that happened in the phase before the climactic eruption. When you read the literature, there's probably 10 times or 50 times as many papers on the climactic phase than there is on the precursor phases. And so it's often considered that this eruption happened as a single event. But actually, this eruptive sequence started in December 2021, and that eruptive sequence that is important in the context of what happened during the climactic phase. So there's a few slides just going through that. So this December sequence, so this is what the islands look like on December 3rd. We've got Hunga Tonga, Hunga Hapai, and the landmass with the crater. On December 19, it was a very explosive event, about 12-kilometre plume heights. The important thing about this event is when the eruption ended, there was a new vent exposed. So the new eruption didn't use the old vent, it used an adjacent structure for that eruptive phase. And through December 22nd through to about December 30, there were several pulsatory explosive eruptions that pushed plumes into the atmosphere. And between January 1st and 7th, the eruption had pretty much stopped, but there was intermittent explosive activity from this new vent. And you can see that the eruptive phase here actually grew the island somewhat. So based on these observations, we can demonstrate that magma dikes are within the shallow edifice. There's a new vent and structure utilised for this eruptive phase, and there was magma water interaction throughout this eruptive period. The implications of those observations is that this eruptive sequence would have mechanically weakened the edifice, potentially fractured it even further, and that increases opportunities for ocean and seawater to infiltrate into those fractures close to the magmatic system. Now, this is the time series I was presenting. Kathleen McKee is responsible for this time series. And this time series is important because the January 13 and 14 eruption was actually a really powerful event of its own right. So I'll just go through this time series just so that you're across it as we start to describe it. On the first time series, what we've got here is the January 13, 14, 15 on the x-axis, and on the y-axis, we've got lots of different time series data. This is a very complex time series. I'm only pointing out the main things that are relevant for this presentation. So on the top here, we've got plume height, 0 to 60, the plume characteristics, very impulsive start. The plume got to 18 kilometres and it lasted at that height for 22 hours. So that's suggesting to us that there's a sustained explosive activity of magma decompression and fragmentation. Now, unfortunately, the wind field at this time was essentially zero in Tonga, so it meant that once that plume formed, it didn't move. It didn't move, so satellite observations can't show us what was happening at the volcano's summit during this phase. So that's unfortunate, but that's where the geophysicists and hydroacoustic folks get excited. And so on these next three time series data, what I've got is the lightning rates. So lightning rates, flashes per minute for flashes within 20 kilometres and within 300 kilometres versus time. We've got the infrasound. So this is the sound waves that are moving through the atmosphere. And we've got the hydroacoustic data. So detections per 2 minutes here. These are all the grey data in these two plots. The orange data here and the blue data here are related to root mean squared amplitudes, which are essentially a proxy for the intensity. So although we can't see anything because of the plume, these remote data sets, and by remote I mean very remote, satellites, the infrasound detectors are 2,000 kilometres away, and the hydroacoustic sensor is in Chile. So very remote. The way that Kathleen has interpreted this data is that the lightning rates are pretty constant throughout this phase, but there's a decrease in the lightning rate at about 1800 UTC. With the infrasound data, what you can see is that there are two sort of pulses of these detections, and Kathleen interprets this as two pulses of activity. And with the hydroacoustic data, what Kathleen interprets about 1800 to be the point at which the vent is in the ocean and the ocean has access to the vent. Now, the reason that interpretation is well grounded is because 2017 Bogoslov volcano submarine eruption started in the ocean. When that eruption started, they had low lightning rates and they had low high frequency infrasound. When that tetrachrome developed and the water had no longer had access to the vent, then they got the increase of the lightning rate and they got the high frequency infrasound back. So here it's the opposite, which is suggesting that before 1800, the vent didn't have open access to the water, but after 1800, the vent was within the ocean. This green line here is a picture taken by one of the Planet satellites, and you can see that the two vents that have been formed in the last decade have disappeared. We've still got the two islands up there in the north. So this time series, January 13, 14, very explosive event, probably what we call a volcanic explosivity index eruption of maybe 4. So it's kind of like a magnitude scale based on volume that we use as volcanologists. And a VEI4 eruption, you might get maybe 3 or 4 of those a decade. So this eruption is pretty powerful. Depending on the mass eruption rate that we use, the volume of this event could be up to 0.4 cubic kilometres of dense rock. And that's equivalent to a cylinder that has a diameter of about 1 kilometre and a depth or a thickness of about 400 metres. So a lot of magma evacuated in this phase. So the observations are that sustained powerful eruption, the vent was submarine, significant magma volume erupted and magma dikes in the shallow edifice, and plenty of time for water to, or plenty of opportunity for water to ingress into the fractured volcanic system. This eruption stopped and there was about a 7.5-hour pause, and we don't really know what was happening at this time. There aren't too many there's not really a seismic network in Tonga that's reliable, so we don't really have any detections there, and the remote data don't show anything, and there's no satellite observations. There are satellite observations, but there's nothing in there. So there's lots of interpretations for this phase that have been pitched, or hypotheses that have been pitched. Potentially, this was the phase where the conduits became sealed and impermeable, which enabled gas to build up again. Or potentially this was the opportunity for the water to really access that fractured volcanic network in order to react with magma and erupt explosively during the next phase. So this is the climactic phase. In most papers, you'll read that it started at about 4 o'clock, but the satellite observations reported by Alexa Van Eaton in 2023 show that there's a little 12.5 kilometre high plume that exists for about 2 hours. So there's actually a little precursor plume before the big event. This time series is quite complicated in terms of what happens with the infrasound and the hydroacoustics, and these red symbols here are all the magnitude 2, 4 and 6 earthquakes that accompanied this onset of the climactic phase. So what I've tried to do here is simplify that for the purposes of this talk. So I'll go through that slowly. So here we've got this 257 to 330 low-level seismic acoustic activity and this little eruption plume that became visible. At 3:45, Horiuchi has detected and reported a Rayleigh wave with the equivalent magnitude of about 4.9. So Rayleigh waves are surface waves. Unfortunately, there's no depth resolution to those, but it's a relatively high magnitude event, and it occurs 15 minutes before this really impulsive start to the climactic phase. From 4 o'clock to 4:14, the plume is ascending into the atmosphere, but things really change at 4:14 UTC. Here we've got a magnitude 5.8 event at about 10 kilometres beneath the volcano, and that signifies the start of really quite complex system-wide behaviour. Zheng et al. In 2023 has reported some seismic transient events that occur at 4 kilometres depth, and these are interpreted to be oscillations in pressure, so pressure increases and pressure decreases at that depth. And he interprets these as magma hammer signals. So kind of like water hammering that you experience in your pipes at home. And although that signal was, I guess, reported, they didn't really have a mechanism to understand that seismic signal. At this time, we've got really significant infrasound pulses and shock waves, and these shock waves are triggering meteo tsunamis, so tsunamis triggered by these atmospheric shock waves. But the largest tsunami that had a maximum run-up distance in Tonga of 40 metres is associated with this 4-minute type period. So there's really significant system-wide changes happening at the volcano in just these 5 minutes. After that, the plume brought constant acoustic and seismic activity, and the plume rises to 58 kilometres, and we start to see the domestic and international cables severed after that. So for the voyage, the Earth science questions that we were interested in answering were what triggered the powerful January 15 eruption? At that time, I don't think we had any sort of concept of how powerful that 13-14 event was. How was the January 15 eruption sustained at high intensity for 11 hours? And how has the landscape transformed post-eruption? And these are the voyage data sets that we collected in order to address those questions. Now, I'm presenting this research as the chief scientist of the voyage. A lot of this research has been done since September, only 6 months or so since we collected those data sets by undergraduates and PhD students. And so our results are quite preliminary at this stage. The first question, what triggered the powerful January 15 eruption? I need to spend a little bit of time going into the background about eruptions and how those eruptions can manifest. So powerful explosive eruptions, there's multiple, well, first of all, I'll say there are multiple mechanisms that have been proposed for this eruption. And those 3 mechanisms are shown here schematically. So the first mechanism is where we've got magma decompressing to shallow level. It either fragments or it interacts with water to result in very powerful explosive eruptions that excavate a crater. So we can call that magma-water interaction or classical spreader magmatic activity. The other model that's been pitched by Dick Henley is this gas-driven hydrothermal seal failure. And so this type of mechanism has been demonstrated quite clearly for eruptions of White Island, for example, and Poas volcano in Costa Rica. And the mechanism here is that there's a series of dikes that are rising in quite a permeable and fractured volcanic system. Now, those volcanic fluids those magmas are releasing volcanic fluids and gases, and they're reacting with wall rock and or circulating seawater to precipitate hydrothermal minerals. So things like the sulfates, silica and pyrite, for example. And the precipitation of those minerals forms essentially a seal. And that seal is very effective at trapping magmatic gases from this overpressured network, such that the overpressure develops here, such that the tensile strength of the material in the seal is broken. And that triggers massive, rapid, almost instantaneous decompression that can fracture the edifice, excavate craters, and result in very powerful eruptions. Now, the caldera collapse-driven model is where we've got magma that's evacuated from the subsurface. That magma essentially is evacuated. It leaves kind of a void. And as the eruption progresses, the roof blocks above that void become unstable, lots of reasons for that, and they fall in to this pressurized system, repressurize it, and it triggers a step change in eruption intensities. So this is a model that's been developed and talked about for a very long time. It fits a lot of subaerial terrestrial large explosive eruptions. And then the last is some sort of hybrid model there. Now, each of these models would predict different signatures in the submarine record, and that's exactly what we were trying to test. And so the data sets that we collected we collected some seafloor stratigraphy in those cores to understand if it's just a single pulse of sediment flow or multiple pulses. We looked at the ash morphology because ash morphology can tell us about magma water-driven fragmentation versus just magmatic-driven volatile fragmentation. The juvenile class density tells us the state of the magma in terms of its vesicularity at the time of quenching or fragmentation. The alteration mineralogy, the assemblage of those minerals, can tell us the proximity to deep intrusions and hopefully explosive source depth, maybe the 4 kilometres where those magma hammering was occurring. The crater architecture can decipher the explosive excavation of a crater versus caldera collapse. And the multidisciplinary time series is really a supporting data set that we can use to test those hypotheses. Okay, so this is some work done by Sebastian Ferrero, San Jose State. We collected at least 80 different cores. We collected them close to the volcano. We collected them 85 kilometres away. We collected them in all sectors where this sediment blanket is. Juvenile clasts derived from the magma represent 90% of the total volume in all the cores that we've looked at. And that ratio of 90% juvenile clast versus 10% lithic clasts, it's actually equivalent to what they've recognised in the tephra deposit that's on land. So it's about the same. So that's telling us, or the implications for that, is that if the lithic volume is 6.8 cubic kilometres, the edifice volume, that volume that was in that giant hole, it means that the juvenile volume has to be much greater than that. Maybe not a factor of 10 or 9, but definitely far more than 6.8 cubic kilometres. That volume, maybe, I don't know, something 10, 20 cubic kilometres, whatever it happens to be, is difficult to explain with a mechanism of just simple cratering through the hydrothermal seal mechanism. And it means that there's significant magma withdrawal from the reservoirs, the deep-seated reservoirs implied. The other thing that we've seen in pretty much all the cores is that there is lots of ash. So all of this is ash. It ranges from ultrafine, probably micron scale ash, through to, I think the coarsest class we saw 3 centimetres, but most of it was less than 5 millimetres. So the sediment seafloor blanket is composed of volcanic ash. And that's the same on land. I think that on land, the largest piece they can have identified is a centimetre. This ash is telling us, so ash is best produced when we have interaction of magmas and waters, magma and water, talk about that in a minute. So the cores are telling us that this magma-water interaction mechanism was very important consistently throughout that whole eruptive phase. And the cores are variably stratified, and there's a lot of cross-bedded stratification in here. So for example, this section is cross-bedded, and that's just telling us about maybe dilute density current, dilute sediment flow transport, and lateral transport of that ash material. Okay, so this is a slide that Rachel provided a presentation of which I summarised into one slide. And Rachel is the expert in magma-water interaction and the signatures that it leaves on volcanic ash particles. But I've tried to simplify that story here for this presentation. And generally, when we get the interaction of liquid water and hot magma, the rapid heating of that water generates pressurized fluids that fracture the magma at really rapid speeds, like microseconds through shock waves, and those fractures develop through thermohydraulic processes. And so when those fractures develop, those fractures develop because of the rapid heating of the water, inducing that rapid pressure change and rapid volume change, which then propagates that fracture. And this is a science that is called fractography. It doesn't apply just to volcanic glasses. It applies to ceramics and all sorts of other materials. And Rachel has done a lot of work on ash morphology from different eruptions that are dry and wet across the whole range of composition and at different eruption intensity. And Rachel has developed this damage fracture index, which essentially categorises the fractures. Importantly, these high relief fractures, which indicate really rapid and highly energetic fracturing, and the abundance of those fractures. And so that's called the damage fracture index. And of all the eruption deposits that she studied, Hunga submarine deposits have the highest abundance of these high relief fractures, indicating the most energetic style of thermohydraulic fracturing that has been seen. That's also telling us about that magma-water interaction. So for the sediment cores the ash in the sediment cores that we've looked at, there's a really high abundance of fine ash particles. Most of the volume is ash, highly efficient fragmentation and ash production. The dense particles and the vesicular particles have equivalent intense fracture damage. So that's telling us that the magma-water interaction that produced those ash particles is happening at various levels in the magmatic conduit, before the magmas had a chance to vesiculate, allowing those dense clasts to have the fractures. But the most vesicular fragments, so they're going to be at the top of the magma column after a long period of vesiculation, they've also got the same damage fracture index. And so it's just telling us that the magma was in a various state of vesiculation when this magma-water interaction happened, and that depth window is probably anything from a few hundred meters down to multiple kilometers, maybe a couple of kilometers. And I think I've gone through all of that. Yeah. Okay, so we haven't quite done our homework yet with the juvenile magmatic class and what textures they preserve. Qualitatively, we see a range from dense class. I think this is 200 microns, this scale bar. There. The things there. So qualitatively, what we see are these dense ash particles with just a few vesicles and these highly vesicular ash particles. And qualitatively, I think that there's a greater abundance of these dense glassy clasts than the vesicular clasts. So the way that we're sort of explaining the ash morphology, showing that magma-water interaction, regardless of density or vesicularity of these particles, is that here we have a magma column. This is magma that's rising in a conduit. As it's rising, it's decompressing. The magma gets supersaturated in magmatic volatiles like water and CO2. At shallow level, it's mostly water. We get the bubble nucleation of magmatic water here. And as the magma continues to decompress, those bubbles grow. They grow because of decompression, but they also grow because there's water diffusing from the melt phase into the gas phase. And so these bubbles grow. And on land, this magma foam develops at relatively shallow level, so just a few hundred meters. And at some point, the magma fragments, maybe because the overpressure inside the bubbles exceeds the tensile strength of the magma, and that material fragments. So the way that we're interpreting an abundance of ash dense particles with those high damage fracture indices is that magma-water interaction is occurring along this whole pathway of magma vesiculation. So anything from a few kilometers depth down to a few hundred meters. Now, there's just a paper published really recently, like in the last few weeks. Ji Wu from Auckland University of Technology, who's been working with Shane Cronin. She has really been responsible for the geochemistry and the petrology of these products. The most recent paper talks about how they're using the residual magmatic water in glass to infer the pressure at which the magma fragmented. And one of their interpretations is that these glass water contents are quite high, suggesting that the magma quenched before complete degassing and implying that fragmentation is occurring at elevated pressure, sort of deeper within this conduit. So that's consistent. Now, the other thing I've had an undergraduate do just in the last 6 weeks is have a preliminary look at some of the lithic class in these sediment cores. And so, where to start here? And so one of the things we recognised on the ship is that when we were looking at these sediment cores and we were having a quick look at the ash grains, we recognised that there were some kind of peculiar minerals that we didn't know what they were at the time. So we could see anhydrite, I think we knew what that was. We could see pyroxene and all the feldspars. These are the lithic class here. These are the vesicular juvenile class. But there were these other minerals, such as this sort of greenish one and this kind of blue looking one. Doesn't look blue here, but it's this iridescent blue. And we didn't know what those were at the time. So Max has done some petrography and some automated mineralogy, trying to understand what that mineral assemblage is. Well, as of just yesterday, he said that the automated mineralogy had identified Hedenbergite, which is an iron magnesium pyroxene, ilverite, which is a calcic felsic mineral, chlorite, cummingtonite, which is a iron-rich amphibole, sulfates such as anhydrite, pyrite, quartz, cave feldspar, and albite. So this, at least this preliminary work, the presence of Hedenbergite and ilverite are minerals that they find in iron-rich reduced fluids, high-temperature fluids. So those minerals are precipitated from those fluids, and that's consistent with high-temperature alteration around intrusions. And so this is kind of some really exciting initial information for us. It's potentially, with a bit of quantification, we might be able to use the pressure, temperature, and salinity conditions to understand the depth at which these minerals were exploded and liberated. So on our voyage, we did do some seismic reflection surveys, but in 2024, Cornel Durand and his team also did some seismic reflection surveys, and they've reported results at ANU last year on a few profiles, I think, trying to understand kind of the structure of this crater. So in a scenario where we think that caldera collapse is a viable mechanism for this eruption, there are multiple ways in which we can form collapsed calderas. So you've got the eruption of magma that forms a void, and you've got the rock roof block subsiding into that void along structures that we call ring faults. Now, we can have sort of a massive roof block failure, or we can have like a downsag type model. These have all been observed on land. Or we can have kind of, what's this one called? The downsag model, or we can have kind of like these stepped blocks that represent the caldera floor. The important thing for any model is that we've got structures, and on those structures there is a noticeable displacement. Cornell's preliminary data have yet to recognise those structures, and instead it looks like the summit crater looks like a carrot-shaped hole rather than a caldera. In order for us to move towards that caldera mechanism, we absolutely need to see those ring faults, and they're not observable with the current seismic reflection data that we have, or that Cornell has. We have complementary seismic reflection data in different orientations, and we'll be testing that hypothesis with these new data when they're processed. So at the moment, the caldera collapse model doesn't have legs. It's not viable at the moment with the current data. Oh, and that's just a close-in of these two units defined. Okay, so the working model for the trigger of this event Very preliminary because we've not really quantified any of our data yet. But from discussions that we've had in our group, this 15-minute precursor Rayleigh wave is suggesting that fractures are opening. That's the interpretation, and potentially that fracturing is allowing that water to ingress into the volcanic edifice, as is shown here. The magma hammering event at about 4 kilometres depth is also telling us that at that depth there are structural changes. And so I think that the data at the moment are telling us that the hydrothermal system is actively fracturing prior to the climactic phase. Rachel's data demonstrates that magma-water interaction is occurring to fragment the magma in a really fine-scale way to liberate all that ash. And based on all the cores, it looks like that text, or based on some work that Rachel's done, it looks like that mechanism is consistent throughout the eruptive phase. So the working model that we'd like to pursue is that this fractured hydrothermal decompresses. It starts that cratering process, and that cratering process allows seawater to ingress into this very hot magmatic hydrothermal system to result in very explosive magma-water interaction. That further increases the excavation of the crater, but one important thing it does is it starts to reduce the confining pressure on the deeper magma reservoirs. So those magma reservoirs are also being decompressed, and that's driving the circulation of the magma and ascent of that magma to shallow level in order to sustain this eruptive event. Rachel's provided this very nice graphic, which is kind of demonstrating this process quite well, in that down at depth at high pressure, we've got a non-bubbly melt sitting in the edifice, and as magma decompression begins, the magma becomes a foam. Water ingress into those fractures can trigger those thermohydraulic shock waves that fracture the magma, and this happens on really fast timescales, and it can fracture the magma across this whole decompression path, liberating juvenile clasts that are both dense and highly vesicular. Okay, so this isn't just a schematic model that we've come up with. One of the exciting things, I think, that hasn't really been addressed much in the literature is how these gigantic diatreme breccia pipes associated with porphyry systems develop. So economic geologists working in porphyry systems have recognised for a very long time that there are diatreme breccia pipes that are carrot-shaped holes in the earth that often terminate at the top of a porphyry system. Here is the Tumbangpitu Tujabukit breccia pipe. Now, this breccia pipe is about 2 kilometres wide and 3 kilometres deep. And in that breccia pipe, there are juvenile clasts, there are lithic clasts, and there are clasts of the actual porphyry. Some of these clasts are absolutely ginormous in size. So you can kind of see that big clast there, that big clast there. That is a giant excavator full scale. Now, the conceptual model from the economic geologists is that somehow this magmatic hydrothermal system becomes destabilized. It triggers an explosive fracturing of the edifice that triggers explosive decompression-driven fracturing. And at some point, as these fractures are being developed in the forming pipe, it allows water to ingress to enable those magma-water interactions. So that's been their conceptual model. It's been their conceptual model for a long time, but it hasn't had the attention of volcanologists. And so this is something that we think maybe has similarities to the architecture of Hunga. And we're here to try and understand what observations and measurements should we make here in order to constrain some parameters that help us with the numerical modelling of the fracturing process above magmatic hydrothermal systems, how those fractures develop, how do they close, how do they allow water to interact with that magma to create these giant diatreme breccia pipes. Yes, and that's one of the reasons why we're here. Okay, well, that's pretty much where we're at with the trigger story. At the time of pitching this talk to Thomas, I was also hoping to present some material on how this eruption was sustained and how the seafloor is changing, but our group just isn't there yet. But thank you for your time. Very happy to answer any questions.
Thank you, Rebecca. That was really interesting, and I guess that we don't always see much volcanology in this room, so it's very refreshing, for us to see what those analysis and the work that is being done and how we can trace the patterns and mechanisms of an eruption. So yeah, thank you for that. Any questions? Yeah.
Hi. In our experimental lab, we often take silicate magmas and crunch them into water, and they don't shatter into ash. So is this a question of scale? So do we just need a large enough bucket and a large enough blob of magma, and eventually it will shatter into ash?
Rachel?
So it can come down to, so there's different magma water interactions. There's the one that's driven by that thermal hydraulic fraction. And as you've got your water being heated and rapidly expanding, it's got nowhere else to expand to other than like driving forward, driving that fracture. If you're just dropping something hot into a bucket, you can have that slow thermal quench sort of happening, and you'll have some fractures open up. You might even damage some things quite intensely, but it's very small. There's not a lot of extra particles you see formed. It's only a few little bits, and most of it's just quenched glass with nothing extra to it. So it's not just scale, it's not how that water is actually, how restricted the confinement of that interaction is. If you can just have that water expand, say, upwards away from your hot body as it's heating, you can't drive that fracture with your heating.
I've also tried the same experiments with hot pumice and hot bits of obsidian and things like that. And yeah, it's a bit disappointing.
You mentioned that it's a lot about vapor and a lot of gas. You know the composition of the gases, like CO2 or SO2 or like that?
Yeah, so that's a good question. I believe so the Wu paper, it's very detailed geochemical paper that I'm not completely across, but they were measuring the they were measuring magmatic volatiles in melt inclusions, and some of the water contents were up to sort of 3% for an andesite, and I don't remember reading anything about carbon dioxide. So
No, they didn't do carbon dioxide. They did do some measurements of sulfur because they were trying to do the max balance
okay.
with the games, because one of the things you didn't mention it in terms of time, but there's always been a question of whether this eruption had less sulfur in it than any other eruption
Yep.
around them. So what caused that was all maybe we just don't understand it.
Mm. Mm.
So no, they didn't tackle CO2.
Okay.
I have a very basic question. So you mentioned at the start that the andesitic rocks aren't typically erupt in explosive fashion, and then we end up with this eruption. So the first part of the question is, does this volcano typically erupt this explosively? And I'm guessing the answer to that is
No, although there is another deposit at about 1100 AD that they also think was caldera forming.
Yeah.
But I think since 1100, the eruptive sequence has been those sorts of smaller eruption plumes and island building followed by collapse.
yeah, okay. And then so you come to the mechanism, but for a non-expert, nothing about the mechanism seems unusual. Right? Those conditions should almost exist in most submarine volcanoes. So why is it? I still don't fully understand the uniqueness from that mechanism. So why doesn't this happen more frequently, I guess?
Yeah, I don't think we understand that the how you prepare a submarine volcano for an eruption like that, and what sequence of events do you need to drive such a powerful explosive event Krakatau was probably as explosive as Hunga, and that's demonstrated by mass eruption rates, the damage fraction index, but that magma was rhyolite.
Yeah.
So that's kind of sort of to be expected. And since Krakatau to Hunga, we've probably had, I don't know, up to maybe 10 submarine eruptions since then that have been relatively well recorded, and they haven't resulted in this powerful eruptive pattern either.
Goldilocks thing.
We don't understand. Yeah.
But would you say that it's something from inside the volcano, or it's from something from an outside forcing to the volcano? So in a sense, like, do you start with different ingredients, or do you do different things to those ingredients?
As a volcanologist and not an igneous petrologist, I guess I would err on the side of that the edifice has to be set up or staged. The environment of the interaction of magma and water has to be just right.
Like some sort of geometry?
So some sort of geometry or some sort of permeability or fraction network of the edifice has to be set up in order to drive such a powerful eruptive phase. Yeah. What would you say, Rachel?
So I'm also leaning on the side of this setup of the volcano itself to have like these sort of correct conditions for it. Because I have looked at deposits from other deep submarine volcanoes that were still CEI5, and it doesn't have that intensity of damage on the particles. So while there was an interaction, there probably was a bit of extra material created. It was nowhere near as intensive as we see for Hunga or Krakatau 1883. It seems to this must be a way of introducing, for at least for Hunga, because we certainly see those gas particles without those vesicles in it. So you're breaking material before the magmatic gases have had a chance to do any of that work or even to weaken the material. So you need some way of introducing water deeper into the system before you can have those vesicles get started.
Just a thought following on that. I mean, I don't know how normal it is to have a volcano set up perfectly like this, where you have a very small amount of seawater in the crater, because I mean the water depth will provide confining pressure that would lift the gas in the magma system. So I don't know if that's unusual or not, this system. But the question I wanted to ask was, you talked about this missing 2,800 Melbourne cubic meters of rock. Did you answer that?
Yeah, so it's interesting. So I guess if all our sediment cores on the seafloor and on land have about 10% lithics. So the natural thing to go is, well, okay, the magma volume must thus be 9 times greater than the lithic volume. But that makes the magma volume something like 40 cubic kilometers, which just sounds a bit outrageous. So I've been sort of thinking about that a little bit since putting this talk together. And the only thing I can really think of is that a lot of that edifice actually broke up as very large chunks. And as that material was evacuated into the atmosphere, it came back down into the ocean and slid along the flanks of the volcano. And those chunks of the volcanic edifice are actually distributed around the volcano. And that would accommodate for a lot of the volume of the lithic ejecta. So we don't need as much magma, I guess, in that case. Yeah. But one of the things we're really excited about is looking at how lithic abundance changes through the core thickness. It looks pretty constant from the bottom to the top. So that crater excavation process looks constant. But that's kind of a hypothesis that we're really excited to test with quite a lot of work with those cores.
Well, let me just continue that.
Yeah.
I didn't quite get your volume calculation, because you take a sample bucket of the ash that you get at, and a number of people have looked at the components of that and come up with 10, maybe a bit more percent on the volume of lithics, in other words, not volcanic glass, fresh stuff together. And then you're projecting that means that, yes, there's 9 times more volume than lithics, but then you extend that to say 9 times more than 6 kilometers or so, which was the volume of the crater.
Mhm.
But I didn't quite get how you did that.
The crater volume, I am assuming, is the lithic volume,
Hey, but why would you do that?
because the crater volume is not related to the juvenile component. It's probably related to the edifice volume, largely. There could be dikes or conduits of magma through that top kilometre of material that went missing, but that magmatic volume will be much less than the edifice volume that's missing. Yeah. Yeah, sure. Well, I'm interested. So this is what I was doing when I was saying, here's Hunga, and there's the carrot-shaped hole. And from Marta's work, this much is missing, and that much is 6.8 cubic kilometres. And that in that top kilometre, there could be dikes of magma that extend to deeper reservoirs. But most of that missing volume is lithic, it's part of the edifice. So if in the deposit, that missing volume is only 10%, then the rest of it has to be much greater volume. The juvenile volume has to be much greater.
But you're defining your pre-eruption crater.
Yep.
As 6.5 kilometres cubed.
Yep.
Of lithics.
Yes.
Lithics are defined as metamorphosed or hydrothermal organic materials.
Lithics are the non-juvenile component of an eruption deposit.
Yeah. So
Yep.
they defined it showing mineralogy, which is mainly due to alteration.
Oh, anything. Bits of old andesite that was erupted 100 years ago. Anything.
Yes, that's right. There's an assumption there about what the primary content of the now crater is.
Yes, there is. I don't know.
Yeah, and it's probably a balance of.
Yeah. Yeah. But we agree that the magma volume exceeds the lithic volume. The magma volume exceeds the lithic volume.
Yes.
Yeah. Yeah. No, these are exactly the discussions I'm really excited about.
The wonderful thing about this eruption is that there's so much data on the mass, the volume, and the energetics, which you don't get for eruptions, terrestrial eruptions or submarine eruptions. So all the time you have to deal with questions which you've never had tackled before. So it's really unique. And this is a unique submarine volcano eruption, just one of the places of its scale. Right? Yep. And it's bigger than Krakatoa. So
we're just going to take a last question from Solomon.
I have a very good question. So one of the unique observation of this is that it continued for 11 hours.
Yeah.
I'm imagining that when the explosion happens, the water may be at least the liquid water on top of the volcano somehow be displaced from the crater. So I just wonder what is your hypothesis of how that explosion was sustained for such a long time without the presence of liquid water?
Yeah. I think, I've had this discussion a few times, and I think that the vent was always inundated with water. Yeah, I think that process of exploding the material out of the vent through the water column, I don't think that precludes the ocean accessing the vent. I think constantly there has to be water that's able to access that area. And one of the challenges for the magma water model has been, how do you get the magma to see enough water in order for that fragmentation to be so efficient and that deposit to be full of ash? And with a cratering mechanism, that interaction, that surface area, that highly, or that dense fracture network and that cratering mechanism, it actually helps with the surface area problem. And so I think water was just always had access to that crater. Yeah. And that crater was being excavated probably, I think in Cornell's data, the bottom of that crater is actually 1,500 meters. So that's a large crater. Mm-hmm.
Well, this will conclude today's seminar. So I invite you to thank Rebecca for a wonderful talk today. So as Rebecca mentioned, she'll be around this afternoon and tomorrow as well. So if you want to interact with her, she'll be on site. And we also have a dinner tonight at 6 p.m. at the...
Well, we've actually arranged a program so that the team here will be mostly in physics, and so they can contact